Johnson. I am a structural director with SOM in Chicago. Thank you CTBUH for the opportunity to present 100 Mount Street and the Baker Bracing for the Innovation Award. The Baker Brace is a composite steel and concrete mega bracing system that allows 100 Mount Street to achieve an offset core. This maximizes the efficiency of the floor plate and the views of the harbor. The project was developed by Lang O'Rourke and Dexus. The architectural design was by SOM and Architectus, and the engineering was by SOM and Enstruct. The project is located in North Sydney in the center of the growing CBD. North Sydney is located on a sandstone plateau overlooking the harbor. The hill acts as an escarpment, increasing the wind speed, which is critical for the design of the project. In addition to the escarpment effect, the neighboring buildings create wind buffeting on our building, increasing the wind loads from the code requirements. The building is a 35-story, 143-meter tall office building with retail at the lower 2 levels and parking in the basement. 100 Mount Street has a distinct presence on the CBD skyline of North Sydney with its express structure that really is the architecture for the building. The project uses an offset core adjacent to 80 Mount Street shown on the left-hand side of this building. This allows the project to open up the ground floor plane for both the lobby and the retail experience on the right-hand side. The project engages with the urban environment to maximize the utility for the building occupants and those visiting the building. This is the typical low-rise plan. The offset core is shown on the left-hand side and the mega bracing is to the right-hand side. The floor plate is supported by just 10 columns for the 1,500 square meter floor plate. These columns are inset by 6 meters to maximize the views of the harbor. This is the high-rise plan. As you can see, it's very efficient. The low-rise and mid-rise elevators drop off, and the area is recaptured in the floor of the office plate for maximum efficiency. This does cause some challenges, though, structurally that we'll get into here with the design of the bracing. And here's the view of the harbor looking out from the 6-meter cantilevers. The key plan on the lower right corner shows the position of the camera with a view of the harbor, Harbor Bridge, the Opera House, and Sydney CBD. Now, the entire south and north edges of the building are glass enclosed. This is actually a view from the bathroom, and you can see that the views are incredible throughout the entire building. And by doing this offset core and engaging it with glass on the sides, views are maximized as well as the floor plate efficiencies. And so how would a building like this typically be supported? Well, generally speaking, you would try to take all of the wind resistance in the core. And as you can see, as broad-faced wind hits the tower, if we were to do this, 100% of the wind shear would be taken in the core, and you would have a torsional moment that would try to twist the building to try to contend with. And although this could be possible, it's kind of inefficient. And at the high-rise portions of the building where the core basically erodes to very little, it would be a real challenge. So instead, by introducing the bracing on the right-hand side of the floor plan, now the shear is shared between these two systems, 50% in the core and 50% in the bracing. And this allows the core to not only erode, but be very efficient all the way up and down the building with typical wall thicknesses of 350 millimeters thick. And so these are the two main systems of the building for overturning wind stability. On the left-hand side, you can see the reinforced concrete core rising above 80 Mount, and on the right-hand side, you can see this composite mega bracing system. And these systems are really indeterminate, meaning the load that goes into each system depends on how stiff it is. And so the real challenge with 100 Mount Street here is how do we make this mega bracing system as stiff as possible so that it can not just compete with the stiffness of the core, but really assist the core and allow it to be efficient and erode in the way that it does. And so we looked at this in a number of different ways, starting with topology optimization. This is a density method run looking at where the material is to be placed, moving material from low stress locations to high stress locations, and we get some pretty good results. And we take a closer look at the final results here, the bracing on the left-hand side. You can see that it's kind of an interesting pattern. It's not quite an X brace, it's not a chevron brace, it's something in between. And this is something that we notice quite a bit when we're doing these topology optimization studies. Now, our interpretation from that is that the load is following lines of principal stresses as identified in Mitchell's work with an unbounded Mitchell truss on the left-hand side with a cantilever and a bounded Mitchell truss on the right-hand side, which is very resembling a building and these principal stress flows. And so we understand that these are very efficient systems and can increase the stiffness of that bracing. The bracing geometry can also be solved by hand by looking at applied loads in a free body diagram. And what we know is that the optimal location for an X-brace is not in the middle of the module, it's actually at the 3/4 point, 75% of the height. For 100 Mount Street, because of how the modules of the bracing worked out, it's actually at the 2/3 point, but that's still 99% of the optimal location and very efficient. Beyond just looking at the shaping of the bracing module, we also need to understand how many bracing modules we have in the building. And so this equation is from a paper that was put out by Bill Baker and Lauren Baghini, looking at the height and width of bracing systems. And based on this paper, we understand that the optimum number of bracing modules is 6.9, where Mount Street has 6.5. So very efficient in terms of how it lays out as well. Well, how do we describe this thing? When you look at bracing patterns, if you say, hey, look, a single angle brace or an X brace or a V brace or a chevron brace or eccentric bracing or knee bracing, people kind of get what that is because of traditional structural engineering and the commonplace in the market. But what is this kind of bracing that we're finding is these kind of optimum patterns? Well, it's a bracing pattern that we've used now at SOM on a number of different projects, and all of this work is being led by Bill Baker and his commitment to efficient structures and innovation and optimization, which has led to these different bracing patterns. Now, the top two examples are showing discrete bracing examples that are expressed. The lower left-hand corner is an example where we actually buried it inside the core. We just believe that this is an efficient bracing pattern and doesn't necessarily need to be expressed. It can be placed on the inside as well. And then the lower two right examples are higher node counts associated with them. But because of Bill's innovation and because of Bill's leadership in developing these systems, we've been calling these bracings Baker bracings after him, as is traditional in structural engineering, like Warren trusses and Pratt trusses and Howe trusses, etc. And so here is our Baker bracing system. It is a composite mega bracing system consisting of reinforced concrete columns to be consistent with the base building structure and structural steel bracing. The central node of that X-brace is raised up to be more optimal, and we have connection plates that deliver those loads into the concrete columns. Now, a constructability issue arises once we start mixing materials here, and that's really the movement of the concrete columns. These columns are going to shorten over time. They shorten due to gravity loads, shrinkage, and creep. But there's also compression that forms in these bracings because they're restrained by the floor. And that can be a challenge because the steel bracing, of course, does not want to shrink, does not want to creep. So we have to manage that. And so to illustrate the effect of this, if we were to look at the different load effects, if there's no releases, you would get compression in these brace forces due to column shortening. And then you have to add on top of them the brace forces from wind loading with a combined force for what we're calling 100%. You can see that the tension in the braces from wind is almost completely overcome by the column shortening. But if we're able to release that creep stress, there's no load from column shortening whatsoever. And then the bracing forces that we have to design them for are just for wind loads. And it actually reduces the forces by about 50%. So we wanted to explore what this meant a little bit more. Early in concept design, we looked at a finger joint detail, and this would allow itself to slide left to right on the page while resisting the overturning vertical shear component. And by doing that, it allows the columns to shorten, and then the braces just lean towards each other, but because they have this finger joint, they don't push against each other and develop compression forces in the braces. As we developed the detail a bit further, we ended up using elastomeric bearing pads so that they would always be in contact with each other, and we didn't have to worry about surfaces sliding against each other, just deforming those elastomeric bearing pads on the inside. We also allowed these pads to be observable in the future with removable cover plates so that they could be maintained or replaced if necessary. This is a diagram showing the three-dimensional components of this central sliding node. On the left-hand side, you can see all of the gray components are steel. The white components are steel as well, but there's slotted fingers into the main gray portions. And on the right-hand side, you can see the interior of the node, as a cutaway, where the gold elements are these sliding elastomeric bearing pads. This is an exploded diagram showing the different components. And really the major force transfer happens at these milled steel finger plates, the white elements. Those are the fingers that were shown in the conceptual detail of what it took to make them real in the final building. And those things sandwich those elastomeric bearing pads and keep them in firm contact for the life of the building. Because the intent of the bracing was to really be very sleek, and here were some renderings that were done at design development and what that node was to look like. You can see there's a gap in between the two node halves, and that's where the compression load is relieved as those braces move towards each other. So now getting into the construction of the project, as I mentioned, North Sydney is founded on a sandstone plateau. It has 6 basements, and as you can see, there's no shoring or retention system. You just saw cut directly into the sandstone, which is, a real challenge in and of itself, but then the foundations are quite high capacity. On the right-hand side, you can see the reinforced concrete core that is founded only 3 basements in, where the rest continue down lower for parking. Here's the bracing as it starts rising up. The core on the left-hand image you can see is the first element leads, followed by the reinforced concrete floor plates, and then followed on by the steel bracing as it goes on floor by floor. This is the node of the bracing being installed. On the left-hand side, the rusty metal bits are the elements that are encased inside of the concrete mega columns with shear studs. The elements that are prime painted are outside. On the right-hand side, you can see the node that's exposed after it's cast into the column. These are some of the nodes that are delivered on site. Those yellow components keep it from sliding and locking it into the right position, because we don't want to lose any of that ability to relieve column shortening before it's installed. And you can see there's a little black architectural seal there that prevents any weather or bugs or animals to get in there, and they're protected during the construction phase. Here you can see the bracing and nodes being installed with a couple of tiebacks back to the main building. And on the right-hand side, these cover plates that snap together and conceal the whole thing are being placed with just a little screwdriver. And here's the final look of it. You can't even tell that there's different pieces of metal between the milled steel finger plates and the main node elements. It's just a sleek overall joint that is both serviceable, simple, and efficient structurally. Here's a view looking out from the building at one of the upper floors where there's a hole opening in it for tenant connection level to level. And you can see the bracing in the distance and the size of the gap, as well as some of the cantilevers to the right-hand side and the Sydney harbor below. And again, taking a look at the construction, you can see the core leading, followed by the concrete floors, followed by the mega bracing. Here's a construction photo where it had essentially topped out, and this really shows you how prominent 100 Mount Street is on the skyline of North Sydney, and those wind issues as it sticks up above its neighbors kind of exposes its broad face to the winds. And the mega bracing as the architecture of the building, it's really there as a necessity. It's there to make the core efficient. It's there to allow the core to erode and to capture the floor plate. But the building celebrates it as the architectural expression of the building, one that's rooted in science and efficiency. And the building itself really does stand alone in the skyline. It does rise above its neighbors, and it's got some pretty impressive views from the street level. And it's a building that's really honest in its expression, with just these few materials: steel, concrete, glass, and aluminum that bands the tower. So that's the project, and that's the system, the Baker bracing. We've submitted it for an innovation award because it's not a one-off thing. We've found that it's very efficient and it's very sensible to use on a number of different projects. 100 Mount Street was the first project to realize this, and we've kind of demonstrated in the real world here its advantages and its benefits to the system. And we're happy to present it here today to not only show it off, but to make it available to the rest of the design community as a smart and efficient structural system.